In the last few sessions, we focus our attention on dielectric slab waveguide. We model it in the XYZ coordinate system, but a piece of optical fiber is a cylindrical wire, so that in this session, we're going to do our analysis in the cylindrical coordinate system. So we're going to use the technique we learned before to analyze a cylindrical dielectric waveguide. This is a photo I show you on the first page of this lecture, where you can see that I'm using a laser pointer, and I inject the laser into a plastic fiber. The plastic fiber guides the optical radiation from one end to the other end. In this session, we're going to model this phenomenon by using this cartoon. So we have the cylindrical waveguide in the region 1. We call this the core region. Outside this core, we're going to have a cladding region with a refracting index of N2. And the radius of this cylindrical wire is the A. And to simplify this discussion, we're going to remove the phi dependence of this field inside this waveguide. So let's take a TMO as the one example. Suppose there's a TMO field propagating inside this optical fiber. And we write down the electric field along z direction like this. And again, to simplify the discussion, we remove the variation along phi direction. Since this wave is guided inside, therefore there's a propagation constant along z direction, and there's R dependence of the field. Let's put down this equation into Helmholtz equation. So the dispersion relationship is given by this h squared equal to gamma squared plus k1 squared, because we'll be focusing the analysis inside this region 1, where you have the material parameter epsilon 1 and mu 0. Just assume that this is non-magnetic material. So the dispersion relationship is given by this expression. And in the cylindrical coordinate system, we already figure out the general solution for a standing wave along R direction and propagation wave along Z direction. The general solution is given by this phi of phi and also the R of R. If you multiply these two together, remember that when we try to solve the cylindrical Helmholtz equation, we use the separation variable. And for the phi dependence, we have such an expression. But again, we set n equal to 0 just to simplify the discussion. So the phi of phi is going to be a constant. But for R of R, you will have a general solution with the J and also n, which are the Bessel function of the first kind and second kind. And because we choose n equal to 0, so we set this n equal to 0. And remember that we have a Bessel function like this to describe the standing wave along R direction. But for this Newman function, it involves the solution involves R equal to 0. For this Newman function, R equal to 0, this Newman function diverges, so we cannot take it as one solution. So let's just cross this Newman function out, so that the general solution for the field Ez inside the core is given by this J0HR, and again this H is the eigenvalue along R direction. If you have the Z component electric field, of course you can calculate all other fields. For example, the phi component of the H field is given by this expression. Now we are in the position to look into the solution for R larger than A. In other words, the field outside the core is going to be an evanescent field. So let's first write down the Z component electric field like this, and the field, of course, propagate along Z direction with a propagation constant equal to beta. then again, you put this expression into Helmholtz equation. Then this K is the relevant to the second material. So you have to label this K as K2. So you have the dispersion relationship like this. Now, you have to pick up the right solution for the field outside the core, because the field outside core comes from an evanescent wave. So this means that you need to choose an imaginary number for this eigenvalue along r direction. And let's just denote h equal to j zeta, and so that you have such a dispersion relationship. And this zeta is comparable to the alpha when we talk about dielectric slab waveguide. Because when we talk about dielectric slab waveguide, we make sure that the field outside the waveguide is an evanescent wave. Therefore, we choose h equal to j alpha. Well, similarly, you have an evanescent wave outside this core region. So this h is chosen to be j zeta, which is a pure imaginary number, so that this zeta is the decay constant for the evanescent wave outside the core of the optical fiber. And so now you can write down the general solution for the field outside the core of the fiber. And again, we choose n equal to 0 so that there's no variation along phi direction. Once you choose n equal to 0, then you can label this n as 0 along the r direction. So along the r direction, you want to choose a solution that is consistent with the evanescent wave. But you have to drop this I0 zeta r, because for large argument for large r, this I modified Bessel function of the first kind will diverge. And we are talking about the field that could extend to infinity for r, so we have to remove this solution. This solution is just non-physical. So you keep this solution, therefore you have this result for the r of r. So in general, for the field, for the easy field outside this core region, you have such an expression. With a non-easy component, of course, you can calculate all other field components. For example, the phi component of the magnetic field is given by this expression. So we have the general form of the solution for the z component electric field. Now we want to match the boundary conditions. The boundary is at r equal to 0. So the tangential component of the electric field will be continuous at r equal to a. So let's just pull out the solutions for the z component electric field versus r inside and outside the core region, and set this r equal to a at the boundary, and you equate this field to this field to get this relationship. So this is based on the continuation of the tangential field at r equal to a. The other boundary condition is that the h component, the tangential h component at the boundary is also continuous. So you take out the solutions for the h phi solution, and then set r equal to a into these two expressions to get this relationship. And then you can combine these two relationships into a transcendental equation like this. And at this moment, I want you to compare this equation with the characteristic equation we obtained from a dielectric slab waveguide. If you compare these two, you see the similarity between these two, because I want to remind you that this J and J prime solutions are sinusoidal-like solutions with the large HA. So this means that on the right-hand side of this transcendental equation, this is nothing more than a tangent or cotangent-like of the function. So these two are just very similar to each other. And on the left-hand side, you see this ratio alpha over ky. And for cylindrical waveguide, this zeta is similar to alpha in a dielectric waveguide because both represent the decay constant of the evanescent wave in the transverse direction. And this ky is comparable to this h because h is the eigenvalue along all direction, and ky is the eigenvalue along transverse direction. And at this moment, we still have two unknowns, which is zeta and h. But from the dispersion relationship we just obtained from the last two pages, we can construct the relationship between h and zeta by taking out this beta square from these two expressions. So you end up having this dispersion relationship. Now you have two equations with two unknown, zeta and h, so you can solve the unknown variables. So let's continue to look into this. So I copy it down to this, and then let's move everything to the right hand side except this zeta. And again, this zeta is comparable to the alpha defined in the dielectric slab waveguide. So let's write zeta equal to this expression and define a variable called v. We call this fiber v parameter equal to this expression. And this definition is going to simplify the discussion a lot. So once you have this definition, then you put this zeta into the characteristic relationship we just have on the last page. So just replace this zeta and zeta by using this expression. Then you end up having this expression. And remember that on the right hand side, this is tangent or cotangent-like function. On the left hand side, you have a square root of v squared minus ha squared. So this means that if you want to have a solution for this transverse or all direction eigenvalue h, then your HA has to be less than this fiber parameter. So this fiber V parameter is quite important for you to determine the cutoff of the mole inside the waveguide. So now let's just plot the right hand side to be those blue curves. Again, you see the tangent cotangent-like curves. And on the left hand side, you have such a monotonic curve denoted by this ray curve. And right at the cutoff, you see that the cutoff value is just exactly the fiber V parameter. So the fiber V parameter tells you where the H value is valid for a propagation mole inside the waveguide. In general, this H value has to be less than V so that you have an intercepting point between this ray curve and blue curves. So similar to the discussion for the cutoff frequencies in a dielectric waveguide, we set this zeta equal to 0 to find out the cutoff frequencies of the mole. So let's set this zeta equal to 0. This means that the radiation start to leak out from the optical fiber because zeta is the decay constant for the evanescent wave. So if you set this zeta equal to 0, then put it into the characteristic relation, you end up having a requirement of J0HA equal to 0. So this means that the H value, the eigenvalue along all direction, has to fall onto the solution of this XOP. If you still remember, XOP is the zeros for J0 of X. And so if you allow the P to run from 1, 2, 3, 4, and so on, then you will be able to find out the cutoff frequencies for the first mole, second mole, and third mole. So for example, the cutoff frequency given by this expression can give you the value for, say, the TM 0p mole cutoff frequency. If you just choose the OP x0p from a table for this J0 of x function. 所以呢，在这一节里头我介绍了如何去分析一个cylindrical dielectric waveguide。那这个cylindrical dielectric waveguide里头的这个分析呢， 非常类似就是 dielectric slab waveguide 的分析。那在这么一个这个圆柱的波导管里头呢，它在轴向呢有一个在跑的波，然后呢在横向上头的话有一个驻波的一个场在那个地方。那这个驻波的这个场呢，在描述上头呢是用这个Bessel function of the first kind 来描述。那在这个外头的，就是 core 外头的这个部分呢，它是一个 evanescent wave， 是用这个 modified Bessel function of second kind 来描述。那同样的，你如果把这么一个这个 evanescent wave 的 decay constant 设定成0，代表说你的波已经开始漏到外头来了。那这时候呢，你可以从它的 characteristic relation 里头呢算出这些 cutoff frequency 出来。那这个是圆柱介电子波导的几个重点，供你参考，谢谢。